Good afternoon. My name is Agne Kadusauskiene, and I'm a senior endocrinology resident at Lithuanian University of Health Sciences Kauno Klinikos. Today is my honor, together with co-author Jonas Gužaitis, to share with you our knowledge and experience related to a research called Algorithm for Automated Food Detection in Thermal and Optical Images for Temperature Asymmetry Analysis. In my presentation, I will briefly talk about the burden of diabetic foot ulcer and possible temperature measurement methods of diabetic feet. Then I will move to our research. Diabetic foot ulcer is a well-known financial burden that requires a lot of medical care. It is estimated that 1 in 4 diabetic patients will develop a foot ulcer. About 1/3 of direct costs of diabetes care attributes to diabetic foot ulcer. Prevention, or at least early diagnosis of diabetic foot ulcer, remain a challenge, regardless of improved medical care. Despite our effort to emphasize the importance of daily self-check to our patients and their willingness to adhere, diabetes comorbidities and complications like retinopathy, physical immobility due to obesity prevent them from daily foot examination. In 1997, a well-known American podiatric surgeon and researcher David Armstrong, together with colleagues, determined that temperature changes in foot can be an early indication of ulcer. Later, it was discovered that temperature differences of corresponding areas between feet of more than 2.2 degrees Celsius is abnormal. More importantly, the increased temperature may be presented even a week before ulcer appears, and treatment of these patients can prevent ulcer development. Recent studies demonstrate that daily temperature measurement might be beneficial for not only early diagnosis and screening purposes, but also for follow-up, prediction of healing status, and early infection diagnosis. Currently, there are several feasible techniques for measuring foot temperature that can be classified to contact and remote. Electrical contact thermometry and liquid crystal thermography are methods that share same crucial limitations. First of all, they both work with only direct contact that may cause infection transition, especially if used in public. They also require response time and are difficult to calibrate. Finally, excess pressure could alter the results. Method that does not require direct contact with skin and was used in our research is called infrared thermography. It is a real-time, non-invasive temperature measurement technique used to produce a colored visualization of thermal energy emitted by the measured site. For many advantages, as being quick, painless, harmless, and relatively inexpensive, it has been in research interest for several decades. It was even called the perfect diagnostic method. Handheld thermometer and infrared camera system are widely used in research. However, using a handheld infrared thermometer is manual and significantly time-consuming process as it is a single-point thermometer. It is also not suitable for the real-time two-dimensional temperature mapping of the overall diabetic foot or for simultaneous imaging of both feet. Furthermore, it is not possible to get these values automatically in real time for further automated processing. In order to overcome these issues, researchers now are focusing on the thermal camera processing system. They are especially suitable for several serial measurements used in the follow-up. However, recently proposed image processing algorithms have significant limitations in the segmentation process or being semi-automated. Our proposed system, method, and apparatus for temperature asymmetry measurement of body parts mentioned in this presentation have WIPO and US patents. This research was funded by Diabetes private company. With this experiment, we wanted to verify our algorithm's accuracy to detect feet outline and localize potential inflammation regions. We used silicone phantom feet with irregular feet position inside the frame. For feet outline detection purpose, two data sets of images with and without phantom feet were used, named accordingly. In order to replicate real patient feet, phantom feet were preheated to reach the natural feet temperature. In our feet data set, we used captured surrounding items like furniture, electrical equipment, and human body parts. This data set replicated accidentally captured images and was necessary in order to test the functionality of feet outline detection. In this slide, you can see several images with simulated inflammation regions. These zones were created manually by heating up random regions of phantom soles with heated metal spoon. Thermal and optical images were captured by the FLIR 1 camera connected with Apple iPad Air tablet. The device was held in hands, and pictures were taken from about 30 centimeter distance. Considering this audience consists mainly of endocrinologists, I will try to simplify the methodology of this algorithm. It is schematically presented in this block diagram. After both thermal and optical pictures are taken, image processing consists of four main steps. First, feet marking and template fitting, then obtaining feet templates with grid, following obtaining temperature maps of feet, and finally creating temperature difference maps. After these steps, inflammation region analysis is performed. I will briefly explain you each step of image processing part of the algorithm. Thermal and optical images are captured simultaneously. However, there is a notable displacement in both images caused by an offset of camera focus centers. Therefore, the optical image has to be shifted according to the thermal image's position to align the outlines of feet in both images. Then, foot outline is localized by applying the appropriate transformation to the base foot template. The inspected foot template obtained during the localization corresponds to the foot outline inaccurately. In order to achieve pixel-wise accuracy, the connection points of the inspected foot template are additionally matched with the edges of the foot outline during the fine-tuning process. After fine-tuning the inspected foot template, inspected foot with the fitted template is created. The same procedure of fine-tuning of the template is performed on the contralateral foot as well. The initial template with grid is applied for both feet. Then, temperature maps of both feet are estimated according to the appropriate set points of interest. Finally, temperature difference map is created by subtracting the temperature values between both feet temperature maps. The created temperature difference map shows the temperature differences between the feet. If the feet difference surpass the medically based threshold values, this temperature asymmetry indicates a possible inflammation region. Analysis of inflammation region was performed by examining the feature vectors. During this process, non-confident inflammation regions were rejected in order to clear the list against accidentally marked non-inflammable regions. For example, the area deemed too small or having considerably small temperature excess. For this task, we used support vector machine classifier. An empty list indicates no inflammation was found, while non-empty list indicates that algorithm has found an inflammation region. We started testing our algorithm from the feet outline detection in optical images. First of all, dense edge points estimation was added to the baseline algorithm, which was performed by doubling foot outline key points to increase foot shape recognition. Then, extended foot shape was performed by using common foot outlines to increase the quality of detection of the base foot location. Therefore, 3 algorithms were tested during the experiment. Later, we tested the ability of our algorithm to detect and evaluate potential inflammation regions in the thermal images. The algorithm analyzed 168 thermal images in total, 17 phantom feed and 98 in no-feed datasets. Modifications of a baseline algorithm improved true positive results by 22.86% and achieved 95.83% accuracy with 92.86% sensitivity and 98% specificity. During investigation of inflammation localization, algorithm achieved 94.28% accuracy, 90% sensitivity, and 100% specificity. We were able to create a completely automated algorithm that is reliably suitable to perceive the shape of the foot instead of distinguishing foot area from the background. The principal task for our algorithm was to determine feet outlines precisely, as this directly affects the accuracy of the final results. We found that blurred foot contour segments in one image can be seen in another. Therefore, merging the edges of both thermal and optical images allowed better detection of the foot outline. Unfortunately, our study had several limitations. First of all, we used phantom feet instead of actual patients with diabetes because of the coronavirus outbreak in our country. However, we believe that phantom feet image data is sufficient enough for the feet outline detection purpose that was the main object in the study. Secondly, phantom feet are ideally shaped, and that may lead to a better foot outline detection results. Study with real diabetic patients is currently ongoing in Vilnius University Hospital Scientex Klinikos to verify these results. Finally, for possible inflammation zone detection, we use asymmetric temperature analysis. This method is based on comparing plantar temperature between both feet. This method is unable to determine the ulceration risk if same inflammation exists in both feet as shown in the picture, and also partial or whole amputee exist. To conclude, we believe that our algorithm could be used for development of a new screening tool with the ability to perform the self-check procedure for presence of any possible feet ulcer. This device could be used in clinics to assist the physicians effectively or during the self-examination in home environment by the patient. Thank you for the attention, and if you have any questions related to our research, please contact me by the email showed in the slide.